Hello and welcome back. In this video, we will discuss Six Sigma operations in the pursuit of lean operations. So it's very difficult to talk about lean without discussing about Six Sigma because lean looks at um, time loss and material loss and of course profit loss as waste, right? So and that's fat to be removed. And Six Sigma is trying to talk about quality. And in a very interesting way, lean kind of associates quality, right? In the pursuit of quality, you achieve lean. And because quality is supposed to be defined as meeting specifications, of course, at the lowest cost possible, at the fastest time possible, right? Without incurring uh, wastages, material wastages, time wastages, human wastages, and all that. So it is inevitable that we discuss Six Sigma. You might have heard of Six Sigma in discussions or subjects around quality. Yeah, and that kind of quality means you also in the same sense that we have quality if we meet specification. Of course, cheap and good value for money goods and products, we have lower specifications. Yeah, think of a toy, right? Ultraman, for example, right? Cheap and good, meant for kids, play and destroy, play for an hour and then limbs, head fall apart. Uh, it has to be small, right? And it is all made of plastics, and the limbs are straightforward. The color is maybe one color only or something like that. Yeah, so it's cheap and good, and of low specification. Let's just look at the height of the Ultraman, right? It's very short. So use less material. So the specification is smaller. So the number is smaller. For example, the height of the Ultraman, it is 5 centimeters. Okay, good. But you've got to produce to spec, right? You don't have a production line that produces 50 centimeters huge Ultraman and then try to sell at a low price, and then you of course will be wasting material because uh, you will incur losses. And if you try to sell at high price, whereas a mom fetching a 2-year-old, 3-year-old kid wanting a $1 Ultraman, finding it very fun and useful, will not be dishing out $50 for your 50 centimeters really huge Ultraman with a lot of colors that even big boys also like, right? Will want to buy and wouldn't mind forking out $100 to buy that very beautiful Ultraman, very sizable, very huge one, right? So each has its value, and we're talking about quality in terms of meeting the value. So it is not about wow, it looks very good, right? So therefore it's high price. It's about yes, it's got high specifications, right? The paint has to be very nice, the plastic has to be of high quality, non-toxic, um, and so on and so forth. And it's transformable, and there's a light beam, there's an LED, and there's a circuitry, and all that stuff, right? So it's high specification versus a very simple 5 centimeters, $1 Ultraman toy. Yeah, so that's low specification. So Six Sigma is talking about um, the very much like Kaizen, right? So Six Sigma is about talking about quality, making sure that you're producing, meeting the specification goods again and again and again and again and again and again, right? So it is very production oriented. When you're a producer, when you're making things, you are supposed to make the same thing and meeting the specifications a million times and all the times within the specifications. That's more like a producer kind of perspective. Kaizen is more on a company-wide culture thinking, um, background thing, right? So it's more like a philosophy. But then both are trying to, uh, focus our thinking, our sort of center of action around quality, around meeting specs, around improvements. Okay, so here I've highlighted these as the so-called central thinking. So first thing, definitely remove defects. It's very defect oriented. It is very producer oriented. So producing what? Producing anything at all that is meeting the specification. So at first you must have a specification. Then you start to produce. Then you have some that meet specifications and some that don't, right? Those that don't, no matter how good looking they are, no matter how repairable they are, they're considered defects. Yeah, very, very simple. It's a yes or no thing. Is this good a defect or not? Right? So remove defects. Very, very central to Six Sigma thinking. So if you're never thinking about defects, you're never counting the defects, then you're not Six Sigma at all. You're not even like breathing Six Sigma, right? Next is reduce variation. So if you make a million units and all of them are meeting specifications, so all of them, there's zero defect, right? Not good enough. You have to reduce variation because specifications simply imply that, for example, a 5 cm Ultraman toy, that's our initial design, that's our initial specification. But during production, there's always a plus minus tolerance. There's always a plus minus tolerance. If you arrange a time to meet a friend, you will say, let's meet at Starbucks at 3 p.m. The implication, the implied meaning is, let's meet at Starbucks plus minus 5 minutes. Sometimes it's plus minus 1 hour, right? I'm sure you have that kind of friend. Okay, yeah, let's meet at Starbucks Orchard Road, right? At 3 p.m. and then 4 p.m. then he arrives. Habitually, right? So that's a very bad defective person in meeting appointment times. But so the idea, I think I was talking about introducing the meeting time more to suggest that even though we say we meet at 3 p.m., there's an implied tolerance. There's an implied social plus minus 10 minutes, right? If you're late for 10 minutes, you probably don't feel so apologetic. Hey, hi, you're here already. I'm not late. I'm just 3:05. Still okay, right? You try to explain and becoming defensive. But if you're 3:20, and then by the time you arrive at the meeting spot, you feel a little bit guilty conscious, right? You feel you are supposed to first offer a reason. I think, I hope, if you're at least socially conscious, you will feel a bit obligated, right, to explain why you are 20 minutes late. Whereas if you're 3 minutes late, you won't feel so guilty conscious, right? You won't feel that you owe your friend an explanation for why you are 3 minutes late. So reducing the variation means that you want to, even though you're meeting spec, you arrive at 3:03, whereas the social norm is, plus minus 5 minutes, right? You arrive at 3:03, no problem, right? But is it good enough? Because you're giving an impression that you are late, right? So you would tell yourself, okay, fine, I don't have to explain, but yeah, next time I better come earlier because this is a job interview, right? So the appointment time is 3 p.m. and yet you arrive at 3:03. What an impression you're already giving. The negative type, huh? Right. So you will vow to yourself, okay, the next interview, if I ever receive another one, I will reduce the variation. 3 p.m. means 3 p.m. And what do you do to achieve that? I'm sure you have had that, right? Instead of timing yourself so exactly, you start to give more buffer. Okay, so I'm taking the bus. Well, bus, a lot of fluctuations, a lot of variation that adds to my variation, right? So no, I'm going to take a Grab, right? So I'm going to make a Grab, 3 p.m. and I plan to arrive there. Taking the lift takes about 5 minutes, but I got to register at the front door first, right? So let's say I arrive there at 2:30. So 2:30, you're already at the front door. You're already downstairs. This takes supposed to be a 5-minute lift, but you never know, right? So You will then plan ahead. But of course, the more buffer time you set aside to arrive earlier, let's say you arrive at 12 p.m. right at the office tower for your interview. What are you going to do, right? So too early, that's also a large variation. Yeah. So you want to reduce that variation also. So no matter what, even if you're meeting specification, the idea is you can still improve. You can still Kaizen. Of course, Kaizen is more a Japanese developed philosophy. Six Sigma is more a Western originated philosophy, right? Western as in America, Motorola, right? Motorola, I'll come to that in a while, but a very, very classic story around Motorola for Six Sigma because we're going to give due credit and respect. Yeah. And the third point, use TQM, use total quality management. Yeah. And of course, this part goes back right to the Toyota discussion, Toyota production discussion. Total quality management is more like a holistic term to encompass the fact that we build quality around customers. So you see, the center of attention is slightly different, right? TQM says customer is in the core, is at the center. We must do everything, right, in a lean way to acquire, to achieve customer satisfaction or top scorer, right? Something like that. Kaizen is more like, even if you're not producing, you should look for something. You should have that spirit, right? To actively look for methods, actions, things, raw materials, ways, people, time to improve, right? So, and try all the time. That's the Kaizen philosophy. Yeah. So, also trying to improve quality, also trying to meet specification in a repeatable way, but very different in terms of center of focus. Whereas Six Sigma, defects, right? Defects, variation, and a lot of math, a lot of statistics, very numerical, very number based, and very producer oriented. If you're not producing, then a little bit difficult to think of Six Sigma because it's not trying to say that you should have the spirit to create something so that you can apply Six Sigma. No. So it's very producer oriented. Manufacturers have to know this, have to be trained in Six Sigma. Yeah. So that's the core thinking. Let's put it that way, right? So now that you understood that Six Sigma achieves its philosophy through mathematics, statistics, data sampling, a lot of them. So it's very numerical. Kaizen is more of thinking, a philosophy, right? So a sort of training, a discipline. You try, yeah, and it may not even be measured. It can be that you manage to rearrange your tools so that they are more convenient to you. So you're removing, you're removing mura, unevenness. Hey, that's good, says Kaizen. That's good. That's improvement. Good. Keep at it. Try again. Do some more, right? Think of new things to improve. So that's Kaizen. Also good because when you remove mura, you are reducing waste and you are then able to be either shortening your processing time or reduce your search time for the right tool, right? And maybe you are then able, if you're the bottleneck, then you are even enhancing the overall production line's capacity, right? So that's a very good thing, says Kaizen. But then that's nothing compared to in Six Sigma's view, because you're not producing anything. There's no flow unit. You're just rearranging your tools in preparation for the production. Yeah? And Six Sigma kind of like, okay, that doesn't count, right? I'm going to count on flow units. So that's a primary difference. So now you start to produce, and because you have made the better arrangement of tools, for example, it may be in the kitchen, right, where you have to like change the tools, right, the change the wok, change the cooking utensils and whatever it is, right? All the time. And you find a way to kind of, neatly arrange them in the battle of making multiple dishes, delicious dishes at the same time, right? So a wok is burning, another burner is also making soup, and then there's yet another burner that is making soup and chicken broil and whatever it is, right? And vegetables and steaming salad and whatnot. And you find a way to rearrange the tools, which will then enhance your interchanging of the tools, and they are very neatly placed, even if you're very busy, right? So that's good. That's fantastic. But you got to produce the dishes. Then Six Sigma will come into action. So that's an illustration of the difference between Kaizen and Six Sigma. Okay, so here there's this uh, in the sort of pursuit for defect-free production, right? That's pursuit, which is basically never achievable, right? You have to know that first. If you did achieve that for one day, don't think you can repeat that same successful day 100 days, 1,000 days, right? So just it will occur, or defect will occur in due course. So just so you know, right? So that's the Six Sigma way of thinking. So you got to produce things, and when you produce things, there'll be fluctuations, variations they call it. And Six Sigma theory says there's a common variation. This is like noise, randomness that just cannot be done away with. There's no way to explain this noise. It's a bit like in the kitchen, you're cooking the vegetables and pork ribs and whatever it is, right? And it's making me hungry. And it's like the fire, right? The fire burns, and the flames will be just random. You turn the volume of the gas that goes into the flow rate of the gas that goes into the wok and the burner. Uh, yeah, it will make the fire bigger and smaller, but then the individual flames, the tongues of the fire flames, it's just random. There's no way to explain, and it's also not necessary to explain, right? So we don't need to say, wow, this particular tongue, flame tongue, right? It's so huge that it burnt parts of the vegetable. But that's just non-repeatable. It's just once off kind of thing. So that's just common variation, random noise that we accept as is. And typically, this kind of variation, it has to be very little. So it's like the little bit of jittery that exists, right? That we know is there. We cannot explain it. We also don't have the knowledge to explain it. Basically, it's due to many inter influencing, inter affecting kind of factors, maybe even the Earth's magnetic field itself as well. Who knows, right? And we don't bother with it. So don't spend your time in finding the root cause of common variation. That's the whole idea of categorizing deviations, right? So if there are some jittery stuff, if there are some rough edges, and that is common variation, then live with it. People understand. People in the trade understand. It's a bit like if you have seen those microchip circuitry or wafer production, right? So those AI chips they manufacture, right? If you enlarge and enlarge and enlarge the real chip, right, the manufactured ones, at first it looks like rainbow color, huh? Because the various edges serve like reflecting lenses to diffract the lights, and then you see rainbow colors. But as you go deeper and deeper, magnifying it, millions of times, billions of times, larger and larger and larger, you start to see that the wires that are so straight at a macro scale, right, begin to have rough edges, like the pavement of your sidewalk, start to have rough edges. compared to the circuit, right? The circuit is like the pavement itself. It is like 1 or 2 micrometer wide. It's very, 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 very narrow. But when you magnify it large enough, you see that the edges of this pavement is also very wavy navy. Right? So it's very, very curved, not straight at all. But then you don't have the tools to straighten it anymore. That's it. Right? So the best tool on earth is able to carve out that circuit, that link from one end to another in as straight a manner as possible, as humanly possible. There's no other way. All right. So, and then when you magnify it, you still see rough edges. And that is the kind of common variation we are talking about. Another thing is, of course, if you drive a car and you hold your steering straight, and if you attach a camera and to look at your wheel, all right, it is probably curving in and out a little bit. So much so that at some point you have to move your steering ever so slightly just to make sure that it aligns with what is visually straight, right? Because your eyes are telling you, hey, how come I'm holding it straight, but it's moving to one side, right? So I better steer it back. You're just reacting to it very naturally. But again, it's telling you that there is just some sort of a micro fluctuations. It could be that the little, pieces of rocks in the tar, they are interacting with the rubber tire and shifting it ever so slightly, like 1 millimeter, half a millimeter to the left, to the right, to the left, to the right, but a bit more to the right than to the left, and so on and so forth. Right. And it could be that the tar on the road itself is slanted ever so slightly. Maybe it's engineered to be like half a degree slanted to one side for the rainwater to be collected at the sidewalk, right? We don't know. But even on a very flat road, you drive like that, you will still kind of like feel the jitter of the road of the tire itself. If you don't drive, then ride a bicycle. Right? No matter how straight you think you're holding the handles, you will have to like jitter it left and right just to keep straight. Why? Why? You're riding on a nice hard cement pavement, no rocks, right? And you are having this very nice bike, new tire, and you try to ride straight, right? And even at high speed, whatever speed, you will have to just left, right, jitter a little bit just to keep straight, right? That's common variation. All right, so this is very, very common. But the common variation is not to talk about, not to say that it is commonly encountered, but it is commonly encountered. This common here just means that it is present in all the processes. So if you associate the fluctuation as common, then don't bother. Assignable means explainable. Assignable means we know why this deviation, typically a larger deviation, not the microscopic ones, a larger amount of fluctuation. Oh, I know this because I had a left tire that is not filled to the right amount of pressure. The right tire is correct, but the left tire, that's why I'm veering to the left. Okay, I know that already. I know that's why I'm holding my steering a bit to the right to compensate. So we knew already, right? So this kind of veering to one side, a consistent variation, deviation from the straight line, that's assignable, because I know the cause, right? So this kind of deviation can be identified. If it cannot be removed, then we at least know how to reduce it. That's the managing part of it. So if we cannot remove it, change a tire, so expensive, right? Then at least we know how to manage it. We go to the nearest kiosk, petrol kiosk, and add more air, get the pressure up again, and then we can get straight traveling. So a bit of a formula here, which is actually not much. It's like the observed number of defects divided by the sample size, the total count of observations, right? Then you that gives us the probability of defect. Then you multiply by 1,000,000, then basically you get defects per million opportunities. And of course, they use a little bit of a magnifier here, right? It's called magnifier because it's a multiple, right? So if you look at 1,000 or what do you have here? 200,000 letters, right? If you have 200,000 letters, then we want to say when you are delivering it, right? What constitutes a defect? What constitutes a defect? That's up to us to define, right? Wrong address. For example, maybe the letter is lost. Well, in this case, lost letter is considered delivered to emptiness, so it's wrong address, right? But for example, if the letter is smeared because rain or somehow coffee, soaked through, the deliverer spilled the coffee, lousy, right? Poor service. But even though it kind of made the letters unreadable because the ink smudged or whatnot, it's not considered a defect in this definition. Just so you know, right? So you have to define clearly first what is a defect. There's no such thing as 0.5 defect. Oh, this flow unit, this letter is half a defect. Oh, we'll consider the other letter a 1/3. No such thing. It's either a defective letter delivery or not. Right? So if you have 200,000 sample size, you keep delivering the 200,000. Each letter has how many opportunities to become defective? Well, in this case, you're just delivering. It's either to the right address or wrong address. Then we just say each letter has one, right? So the magnifier is just one, no magnification. But suppose, so that's why we see a 1 here. But suppose we are talking about the delivery from the central exchange hub. I don't know how the postal services work, but let's say they converge all the letterboxes letters into a central hub, right? And then they sort out by district, and then the van will carry all the district 1, let's say, all the letters for district 1 towards the post office in district 1, and then they distribute again. Now we see 2 opportunities, right? Because at the sorting and dispatching at the central headquarters site, there is a chance that it is sorted to the wrong district. So that's one opportunity, right? So that's one. And when it's got delivered to, and if that part didn't create a defect, then it's got routed to the correct district 1 post office. At that point, it can be then delivered to the wrong address. So 2 opportunities. So then your multiplier here will be 2. It's as if your sample size has doubled, but based on the same flow unit. Okay. So over here, it's just a very simple idea to following definitions from statistics, of course, to say the count of the defects that is being observed divided by the total sample size. That will be the probability of having a defect. And then you multiply by, suppose if I have 1,000 letters, then how many will be wrongly delivered or have defect? 1,000. Okay, so this is basically trying to standardize the probability of defect. So instead of saying 0. Oh, my defect is 0.0000, so many zeros, so difficult to exchange information between different factories for the same MNC in different countries and different competitor factories, right? And for research purposes, for conferences where the like-minded Six Sigma experts and manufacturers come together and compare notes, right, on a friendly basis, they cannot. They have to talk like 0.00000. How many did you say? Sorry, let me start again. 0.00, very, very difficult to exchange. So if they say my DPMO is 1, wow, something like that. So everyone understood that, oh, out of 1,000,000, there's only 1 defect, right? Okay, so that's the whole idea. Now, these bullet points are interesting because they are the central action for Six Sigma. Of course, you will attend a course to go through each and every part of it, and maybe there's also a large part on revising, reviewing basic statistics and probability. But here we are not focusing on those, okay? And while we do have to bring in a bit of statistics and even normal distribution, as you can see already, it's a very basic level. So let's talk about these points here. Get processes to have Six Sigma, right? Processes to have Six Sigma. In other words, the machines, the resources, machines, the people, right? The resources have to have the capability first, because process capability relies on individual resource capabilities, which are basically the human teams, the machines. Now, if each resource, each human cannot do Six Sigma, then you don't get Six Sigma, right? So pursuing for Six Sigma is good, but then your process capability has to be there first. For the process to have that, the resources must also have the Six Sigma capability. But then what is Six Sigma capability? Six Sigma capability means if I give you the spec, the specification, for example, a 5 cm Ultraman, right? 5 cm, and I give you the tolerance. So it's a low specification product or good, and in this case, a 5 cm Ultraman. Low specification does not mean that the mean value, the 5 cm here, is small, because I can have a very luxurious, high quality 5 cm Ultraman that is worth $500. Why? Because it's made of gold. Not only that, it is really, in all measurements, looking like the so-called real cartoon Ultraman, where it is oval eye, it's oval eye, and there's this, everything is so delicately crafted that if you use a magnifying glass and look at it, you'll be like, wow, it's even got a belt. The buckle has a logo, that kind of thing, right? So you'll be so impressed when you discover the micro universe around that 5 cm Ultraman, yeah? And it will be worth $1,000 or more. Depends on how much gold you put in there, right? So it's not the 5 cm mean value that we're talking about. It is about also the sigma that goes inside. What is sigma? Sigma is it's like a natural step. If you try to walk straight with your eyes closed, walk 10 steps forward. I go to a basketball court where no one is there, stand at one end, just stand in the center of the basketball field and walk straight for 10 steps. After that, open up your eyes and you realize, hey, I'm veering to one side. So, so every step is giving us a so-called sigma. Everybody, if you have friends, right? You have two other friends, line up together on one side of the basketball field, and you take 10 steps. When you go forward, two things happen. People will veer to one side, right? That's the bias of the direction. Number two, even though we give a fixed count of 10 steps, when you open up your eyes, three of you will be at different ending points. Can you imagine that, right? Because everyone's natural steps is different. You didn't tell me every step has to be how long. Then everyone will be at the same ending point. But no, right? Because everyone's steps are different in natural widths or lengths. That's why when you say take 10 steps, it is going to be ending at different points. Sigma is the equivalent of a footstep length in the production operation. So this machine is trying to cut out the plastic to make a 5 cm Ultraman, right? It has a natural tendency to sometimes cut 4.97 cm, 5.03 cm, and so on and so forth. you get the idea, right? But I'm giving you 2 decimal places. Another machine, also plastic cutting machine, right, can cut the 5 cm plastic ready for Ultraman, but sometimes it is cutting at 4.7 cm, sometimes 5.3 cm. Very bad, right? It's one decimal place, and it's very visible because 4.7, if I'm used to the size of 5 cm, one look I can tell it's a bit short, right? Yeah. So, but for a $1 toy meant for a 3-year-old kid, is it okay to have this kind of poor crafting? Sometimes 4.7 cm, another Ultraman that is also $1, 5.5 centimeters. Right? When you line them up, they're like up, down, right? Totally unaligned. Of course, to adults, it looks bad, right? I mean, it's bad quality, really not paying attention, anyhow cutting the size of the Ultraman toy. But for a 3-year-old kid, I think that's good. And because which machine do you think is more expensive? The one that gives you sometimes 4.97, 4.98, sometimes 5.02, 5.01, or machine B, sometimes 4.5, sometimes 5.3. Which one is more expensive? Of course, machine A is a lot more expensive, right? Because to get to the second decimal control point, you got to be like 10x better in precision control. So just Google around precision cutting machines. They are like a lot more, 10x more, right? Maybe 3x more, 5x more to get your 10x better in sigma kind of uh, precision. So reducing the fluctuation, reducing the tolerance, the resource that is able to allow you to specify very tight tolerance is a very Six Sigma. It's a very capable machine. It's a very Six Sigma machine. So that's the idea here, right? So it's not the mean value, but more the sigma, the fluctuation that is affecting the quality. Yeah, clear? All right. So Six Sigma, to see quality, you got to line up a lot of these little Ultraman. If they all have laser equivalent heights, you shine a laser beam, it goes, just touching the hair on top, right? Straight through the 1 million Ultraman, right? That's fantastic without being blocked at all, and that's great, fantastic, because all of them are aligned at almost exactly, and laser beams cannot tell. Well, that's fantastic. Yeah. But if your human eyes can already tell, they're all like, some of them tall, some of them short, like wild grass growing, so visible, right? Then it's definitely a sign of lack of attention, lack of pride in the work, very poor quality factory, right? Producing all these lousy, poorly controlled lengths of Ultraman toys. And that's a result of this sigma. So this physical tolerance is fixed. Yeah, fixed. So it's like 5 cm, and then you have, depending on your specification. So if it's a low specification, then we may say this is 4.5 to 5.5. But for a gold material Ultraman of meant to be designed to be attracting, um, you know, resource-rich buyers and who want to have those as collection, we're going to sell it at $2,000. The gold that we use is going to be $1,000. But then plus the craft of making all the details of the Ultraman and all that, right? So we're going to sell at $2,000. Then we would want this tolerance to be 4.99 to 5.01. Very precise. Because if it's not so precise, the more gold that is used for the 5.01 will mean that we lose a lot more money, right? Yeah, so we want a very tightly controlled machine, high precision machine. And we want our resource to be able to keep Six Sigma. Six Sigma. So remember, Sigma is the natural step of the process. No matter what, it will deviate to the left, deviate to the right by some sigmas. And we are going to say that this resource, this cutting machine, has to be able to make 6 steps to the left and right. Right? 6 sigma in each direction, the natural way it fluctuates, 6 sigma, and is still within our given tolerance. Then it's a good machine. Then you have the 6 sigma process capability. That's what it's trying to say. Okay, those of you familiar with normal distribution, you will know of the Z value concept, right? The Z value. So no matter what you're talking about, whether it's length, weight, height, pressure, density, energy, whatever it is that you're measuring, you can convert all the measurements into the Z value. And Z value basically is this value, the plus 6, minus 6, plus 3, minus 3. That's it. Very simple, right? So sigma is the natural step. Z counts the number of steps. And Six Sigma says you walk 6 steps, you deviate, you just do your own dancing. You know, you naturally you will go left, go right. You do your own dancing, your own fluctuation. I allow you to move 6 steps to the left, 6 steps to the right, and you're still within my specification, then you are good. Good for my definition. Good for my specification. Yeah, okay. And natural variation is plus minus 3 sigma. Natural variation. That means everything is within plus minus 3 sigma. Very few items will go outside. Okay, so here it'll be 2,700 parts per million. Parts per million outside the limits. Right, so roughly half on the left, half on the right. Half on the left, half, roughly. So we see it, we are using the normal bell curve because whenever you are engineering towards a specification, the whether it's human or machine, it's being observed that it is either overshooting a little bit or undershooting a little bit. Right? So naturally, then it will give rise to a somewhat symmetrical bell curve. But if it is asymmetrical, you tend to move more to the right than to the left. Then it's a biased kind of machine, and that usually is an assignable variation because you know that there's some controls that is being misaligned or whatnot, right? Maybe the machine's balancing legs are being tilted to one side. The fine tuning support wasn't configured correctly, and so it is, you know, slanting to one side in a very microscopic fashion. So only when you make a million flow units, right? You make a million cutting of the plastics, and then you measure the plastics, then you recognize this kind of deviation. So Six Sigma is all about measurements, repeat, find defects, and then you cut down on the defects. Do something to reduce the defects, and then repeat. So Six Sigma, get the process variation reduced from 3, right? Get the process variation to reduce. That means get your given fixed tolerances from left to right. Your steps cannot be big steps, right? When the machine chooses to naturally step to the left and right, just due to its own various fluctuations, common variations, it has to reduce the steps. Your sigma has to be reduced. Another way to say it statistically. So your footstep, all right, because I want you to step. It's like drawing 2 lines on the basketball court, right? So maybe 10 cm to your left, 10 cm to the right. And then we use a colored tape to make it visible, these 2 lines. I want you to make 6 steps to the left and to the right. And you cannot go beyond the colored tapes. Then what do? You reduce the size of your steps, right? If you can. But if your footprints are naturally very big, no matter how, you open up your legs, it's already a wide kind of step, right? Then that is difficult. So no choice, you got to train to make tiny micro little steps so that 6 steps to the left and 6 steps to the right, you're still within the yellow tape or something, then you're fine. Then you are Six Sigma. That's exactly what's happening here. That's exactly what's happening. And of course, to the extent that we don't necessarily reduce our steps in a very easy manner, our step size. We say take 6 natural steps. Then we are going to be purposely squeezing our legs a little bit, not opening up our legs, so that we can make 6 artificial micro steps. Right? And some people even have a tough time doing that. Right? So if you cannot do micro steps, so that 6 steps to the left, 6 steps to the right, you're still within the yellow tapes, you cannot, then no choice. You are not a Six Sigma machine. You're not a Six Sigma resource. And then you may have to be changed. Right? So that's why I say get the process variation reduced. And this is easier said than done. It could mean that this old machine is already, rattling back and forth, right? So when it cuts the plastic, right, its own rattles, the metal hitting the metal itself and whatnot, is adding to the imprecision. So how do you do that? You cannot, right? So maybe you can, maybe you have a little screw to tighten the loose metal. Then you can reduce by 1 or 0.5 sigma maybe. But then if you are already having your sigma is already large, right? So plus minus 6 easily goes outside, and then you reduce sigma by a little bit, by half, by 10%. It still cannot be within the plus minus 6 sigma and still be within the control limits. Then no choice. Then you have to change to a more precise machine. So if you Google around, let's say for the same kind of action, cutting, right? Cutting metal, cutting plastic. Just Google around. Low level, cheap ones, they tend to have bigger sigma. That means they themselves rattle. Not really visibly moving or shaking, but then just that the mechanical arms or the cutters cannot aim so precise. They don't have mechanisms, don't have guidance, don't have anything to make the cutters aim precisely. Whereas expensive ones, they sell expensively. They're also cutting plastics. Why do they sell expensively? Just look for fluctuation, deviation, or tolerance. You'll find that it's a very small tolerance. In other words, if you say it's 5 cm, it will deliver 4.99 to 5.01. Wow, right? Or some might even say if you specify 5 cm, naturally it will be 4.9999 to 5.0001. Why do they dare to claim such a precision? Or because internally there's a laser guided measurement to make sure the cutter, which is blind, right? The cutter is being positioned by the robotic arm, and the robotic arm is guided by the laser vision to make sure it is maybe even molecular level, it is accurate down to several molecules precision, right? So if that is the kind of machine you are getting, then yeah, it's very precise, right? So Six Sigma is also very much about precision. Precision control is a very high tech, highly scientific field that is also statistical, that is also involved in manufacturing. So if you're interested, you can go further in that field. Yeah. So when you specify Six Sigma, when the bell curve is squeezed, because there's no other way, you want all your produced million pieces of flow units, all your million pieces of the 5 cm Ultraman plastics to be cut within, right, 4.99 cm to 5.01 cm, a million of them, a billion of them maybe, right? The only way is to make sure your sigma is so small that 6 times sigma is still within the tolerances. Then in that case, you are looking at 2 parts per billion outside the limits. 2 Ultraman will be extremely short or extremely long. Extremely as in 5.1 is already super extremely wrong. with that precision cutting machine already, because it's supposed to deliver 5.01. So if it's 5.1, it's a big mistake, right? But big mistake. It's a bit like your computer PC, your notebook, right? It is running at 2 gigahertz. So what every let's just say 1 gigahertz, every nanosecond is trying to give it's already executing an instruction, copy the number here to there, read up that memory variable, what's the value, check your camera, read the network port. Every nanosecond is doing that. Okay, right? And it's not microsecond, it's a thousandth of a microsecond. So it's like a millionth of a second. Every nanosecond is doing that. Now, imagine asking computer to wait for 1 second. 1 second. Do you think if the computer can speak, would it say, wow, that's too short? Maybe can I rest longer? Or would it say, how come I have to wait so long? Right? It is like a billion years for me, right? Yeah, because a billion seconds for me. It has to wait a billion times. It could have done a billion instructions in the meantime of a 1 second wait. Yeah, so it's all relative, right? It's all relative. That's why 5.01 cm for a machine to be making a 5.1 cm Ultraman. That's unthinkable, right? That's really outside the limits. Yeah. So if you can make the machine Six Sigma, then you only see 2 parts per billion being produced. LCL is the low control limit, and of course the lower and the upper control limit. And they are defined by the mean value. The mu is here, right? The mu is here. Minus 6 sigma. So this gives rise to the control limit here and the right control limit here. Ideally, you want the left control limit to be better than your tolerance. So if I specify the tolerance is here, then the LCL should be a bit inside. Right now, yeah, because you want to test the limit, right? So it should be inside. And of course, if my UCL is here, then my tolerance likely is here, so that your UCL is inside of my tolerance. Now remember the difference here is customer wants certain thing like cheap and good Ultraman, right? Then the designer designs an Ultraman that has a 5 cm on average, but plus minus 0.3 cm is acceptable. So it's like 4.7 cm to a very rough 5.3 cm, no problem, because it's meant for kids, right? And it's low price, low spec Ultraman toy. So the designer, even though it's from the same company, will set this tolerance. But when it comes to actually producing, the designer who speaks or translates the needs for the customer, right, is no longer involved. It's the production manager, the COO, right, operating officer, or the manager who is in charge of supervising production will do this. And he or she is going to set the lower control limit, upper control limit. So this will, of course, obey the tolerance given by the designer or the customer, but you can also be stricter. Yeah, so that you can have even better quality in the eyes of Six Sigma. And this is just to calculate the probability. Using normal distribution, you can just calculate this probability very easily, just to justify that it is 1 part per billion, 1 on the left, 1 on the right. That means 1 being very short, 1 being very large. Probabilistically, it could be that both are short, but none is large, or both are large. So 2 parts per billion will be defective if you can achieve LCL and UCL. Okay, so converted to Z value, -6 and +6. Right, so this is basically the link between Six Sigma. Why 6 is because of the Z value, 6 steps. Why sigma? Because quality is not in the mu. Quality is in the sigma. If you want to improve the quality, remember quality is defined as meeting spec, right? If you want to improve quality, you're not looking so much at mu, but you do have to look at sigma of the resource or the person. Okay, so that's the whole idea. Now, final example for just to internalize this concept for you, right? Think of yourself as a factory. What are you producing? Your own signature. Now you understand. Yeah? I ask you to sign. Okay, I won't ask you to sign 1,000,000 times, not 1,000 times. If I ask you to sign 100 times your signature, right? Uh, After signing 100 times, actually producing the goods, right? So the resulting inked signature is your flow unit. You are the machine, right? You are the machine that is signing your signature. Once you have signed those, and make sure you sign that on a 100 sheet of exercise book, so that it's always at the same place, at the same corner of the exercise book. And it's very easy for you to flip the pages and not have so much movement that may change your sigma. Okay, so everything is in your favor. You sign and sign and sign from the last page to the first page, because it's very easy to let the pages drop down and then you sign, right? So you sign and sign and sign. After that, you flip through the pages. The signature will start to animate, right? Any deviation will become very obvious, and see if any of those count those that are visibly out of shape. Okay, now if your signature is complicated, just look at one part of it, maybe the curvy part or the straight line part or the last dot that you dot, just one segment of your signature. So use that as a specification of the mean position. Okay, if you're looking at the dot, then we say, what's the mean position of the dot? Always should be like around this part of the page. Okay, then you flip through, you see the dot flickering, dancing, going up, going down, going left, going right. Then you are definitely not Six Sigma, right? You're not Six Sigma because there's so much fluctuation. But if you, some people can do that. If you realize that only one dot is outside, otherwise it almost appears, right, visibly constant. Maybe it floats up and down a little bit. So we give and take, right? Fine, acceptable. It floats up and down a little bit. It's actually not moving. Wow, fantastic. You have very high quality. Why? Because your dot is always on the same place. Only 1 out of 100 is wrong. But of course, that is not far away from Six Sigma. You're supposed to be producing 1 billion signature and have no more than 2 dots out of place. Now you appreciate, right, what Six Sigma is, how stringent this quality expectation is about. Okay, so that's for introducing Six Sigma, right? In subsequent videos, we'll explore a little bit more about this concept. See you then.